Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to look at what are called combinations. So, let me check my notes. All right, we're going to come over to the chalkboard and let's get started. So, today's combinations, so let's put that up here. Combinations. And in a way, we've already done the groundwork to understand this. Okay, so we already laid the groundwork when we learned to see. And that was this. We said that if we have S, E, E, that the number of words that we could write from that said, count up the total number of letters that you have. So we have 3, so that was 3 factorial, but because C is the same as C, it makes an extra copy. It's not necessary, so we need to divide it by 2 factorial. Now, today, we're going to change these letters, and you'll see why in a moment, mostly because I couldn't think of colors that began with E that I had available in my chalk. I do have salmon, I couldn't think of anything for E. So let's change these. Let's change these colors, or let's change these letters first to an R, a B, and a B. And again, if I asked you how many words could you make, you would say, well, there's 1, 2, 3 different positions. So that's 3 factorial. There's a repeat of the B's, so we have to remember that they can be switched. So that's 2 factorial. So in other words, just changing the symbols that we use in no way really changes the problem. It may change its appearance, but not the underlying problem. So now let's make this problem more interesting. And here's how we're going to do it. Let's do this. A jar contains, let's see, R, we'll use red, contains, how about 7 red marbles. And that's why we're using the capital R, or R here. And how about 4 blue marbles. Okay, how many words? Or yeah, let's do that. How many ways can 1 red and 2 blue be drawn? And 2 blue be selected. Okay, I'm going to use this last little bit of real estate here. Hopefully it's be selected. Question mark. How many ways? That's the question of the day. So let's come over here and let's rewrite the problem. And like you may not be surprised, but I think the best way to approach these is for a picture. And let's just draw a picture of a red and 2 blue being drawn. Now, let's take a few pictures that you might have written. Oops. Few pictures. Now, the obvious picture is the one I've already written, and that was a red, a blue, and a blue. But maybe you just didn't want to feel constrained. Maybe you wrote this problem as, maybe you drew a blue first, and then a red, and then a blue. And what I want to show you is that's okay. Either picture works. So now, let's think about this. When I want to know how many reds are available to me, what I would do is I would say, well, if I look back, I have a jar that has 7 of them. So I would put a 7 in this position. And then it says how many blues? Well, we have 4 blue marbles available, so that's going to be 4 blue. And then we're going to put another blue, so that's going to be, there's only 3 left, so there would be 3 blues. Now, remember the multiplication rules as we multiply these up. And it's not the product here that I'm interested in. What I'm interested in is the idea. What if I'd started with this blue? Well, that would have been 4 initially. How many reds were red marbles? Well, there were 7. And how many blues? Now, because we've already picked 1, there's 3. And again, we would multiply. And here is the point. The point is that it didn't matter which picture you drew, because multiplication is commutative. So 7 times 4 times 3 will give you the same result as 4 times 7 times 3. Now, the next thing, we're not done, that's not quite the answer. The next thing you need to remember is this. The next thing you need to remember is that you have a repeat of the b's, because this is just a word. And so you would need to divide by 2 factorial, which is 2 times 1. Or in this case, you could divide by 2 factorial, or 2 times 1. Okay. Now, so this is the idea that we're going to look at now. Now we have more r's and more b's available to us than we did originally when we just looked at c. So let's take it another step. Here we go. How many ways to draw two red marbles? Okay, how many ways to draw 2 red marbles? I'm going to come over here because this is going to take us it's going to need a little bit more space. So let's do this. I'm going to write it as an R and an R. So that's it. That's all I'm going to draw is 2 red marbles. But if we look back, remember that we have 7 red marbles in the jar. So here's what we would do. How many ways can you do this? Well, the first one, I'm going to write it. Yeah, we'll write it this way. A little different. So instead of putting the 7 under the R, I'll just put it over here. So this first R would have 7 marbles in the jar. So now we've taken a marble out, so there's only 6 red marbles remaining. So we'd say that's 7 times 6. And then, but RR is a repeat. It's because it could be RR or it could be RR. So again, we would divide this by 2 times 1. Now, I think that this is a more natural way to do this, but this process comes up so often that there's a deeper pattern to it that we need to show. And that's this. I'm going to put an equals down here. Let's put it here. Now, 7 times 6, it just begs the idea of times 5, times 4, and of writing a factorial would be much cleaner. So let's do that. Let's write this as 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1. Now remember, we did this with permutations. So we said that if we put the 5, 4, 3, 2, 1 product there, we could also put it in the denominator. 4, 3, 2, 1, and we can't forget our 2 times 1. Now, this is beginning to look good, because look at what we have in the numerator. In the numerator, I have 7 factorial. And in the denominator, I have 5 factorial times 2 factorial. Okay, so I'll go this way to save some space. So the question is, we have a 5 in the problem. And the question is, well, where did that 5 come from? And the answer is it came from, we were looking at 7 total, of which we were interested in 2. So we needed to stop our counting after only 2 objects were selected. So the 5, 4, 3, 2, 1 needed to be removed. And how did we do that? We said this is 7 factorial divided by 7 minus 5. 7 minus 2. 7 minus 2 factorial times 2 factorial. So look at what we have. We have a case where we clearly need some other colored chalk. And here's what we need to look at. Pink is a good color for these things. So look at what this is. I'll even just box it so it's clear. This pink part, this was a permutation, and we already saw that. And this last piece, this 2 factorial here, what is this? This accounts for the fact that you can have repeats. So this, and that's what we learned when we learned to see. This accounts for repeats. Repeats, I'm going to put a little bit more, and you'll see why. Repeats or ordering. Ordering does not matter. And I'll explain. Why do we say repeats? Well, that was because we had like C, S, E, E, or C, S, E, E. So the repeats did not matter, but also what it was is it wasn't just repeats, it was the fact that the order of the E's was switched. So that's why we're going to also say that the ordering of the letters in our word doesn't matter. So this is the kind of the heart and soul of what we're after today. And it's so important that it has a formal notation. 7 factorial over 7 minus 2 quantity factorial times 2 factorial. We would write this as 7 choose 2. And we would read that as 7 choose 2. Okay, let's see. Oh, I know what I want to do. This is coming back to me now. Let's add one more dimension to this problem. And I don't think it'll take so long. In a way, I suspect you already will know the answer as soon as I put this up. Here we found out, well, what if we wanted to draw an R and then an R? How many ways could we do that? How many ways could we just draw 2 blues? Well, let's take a look at that. 2 blues. Okay, just drawing 2 blues. We're not even interested in the reds. Well, we could do this problem 2 different ways. We could say that there's 4 blues. And then we've selected one, so now there's 3 blues. And we could also say that those blues are just repeats, or the order of the blues doesn't matter, so we would divide that by 2 factorial. But this is also the same as saying of the 4 blues, I want to choose 2. I want to choose 2. So this is the same as saying 4 of the 4 blue, I need to choose 2 ones. Okay? Now, let's put this all together. We're just about, we need a little bit more, and then we can really take on something interesting. So let's try, what if the problem was all of this at once? Let's come over here. 2 rows. How many ways how many ways to draw, two red and two blue? Question mark. Well, where do we start? I would start with a picture. So let's do that. It doesn't have to be a fancy picture. All it has to be is just one picture that represents two red marbles and two blue marbles. You could be creative. I'm going to be very simple. I'm going to just write, well, I could draw red, I could draw a red, I could draw a blue, and I could draw a blue. All right, let's see how many ways this can happen. Well, I could draw red. That's 7. There's 7 in the bucket or the jar. But now we've removed one, so when I want to select another red, there's 6. Times, now I need a blue. How many are there? Initially, 4, and now I've selected one of those. So then I'm going to select another blue. One has been removed from the 4, so there's 3 left. Okay, but what is this? Why did we make this picture? We made this picture because RRBB is a mathematical word. And so we just need to account for the reordering of the R's and the reordering of the blues. So we would take this, divide that, we would just divide that by 2 factorial for the red, for the reds, and we would divide the 4 times 3 by 2 factorial for the blues. And I'm going to come to the answer here in a moment. We'll put the answer up here, I suspect. But here's what I wanted to show you. Notice that this 7 times 6 over, this is important. So I like, one of my favorite parts about this chalkboard is all this beautiful colored chalk. Like I have this orange. Never seen, this orange has been through a lot of problems. So look at what 7 times 6 over 2 factorial is. Well, let's see if we can see. 7, oh, there it is, right there. 7 times 6 over 2 factorial. Wait a minute, that was 7 choose 2. That's 7 choose 2. Let's rewrite that. Oh my. This piece here is the same as 7 choose 2. And I have a times, and I have this, I have this pretty green. And let's look into this green box for a moment. Into this green box, I have 4 times 3 over 2 factorial. I have then, there it is. I almost forgot. Look at that. 4 times 3 over 2 factorial. We'd already figured that. That's 4 choose 2. So that's the next piece. I should write this one in orange so that it matches. 7 choose 2. Orange and white looks like a creamsicle. And then 4, that's not. And then my next box was 4 choose 2. So here's the point. The point is there was 2 different ways to get this answer. The simple way, I think, is to draw the picture and then just treat it as a word. Treat it as a word. However, as problems become more advanced or sophisticated, once you realize that the pattern can be reordered, you can also use it or address the problem with the choose function or the combination. So either way, we should get the right answer. Notice that 2 times 2 is 4. The 4 cancels. The answer is 7 times 6 times 3. Multiply all that up together, and I think we get 100. No, I don't think that's right. Yes, I think it is. 126, I believe, is our answer. So, what have we done today? These are called combinations. But we're not done. We're actually warmed up now. here. The question is why? What would be a good example? And the best example, it's a difficult one, but we're ready. The best example is poker hands. Poker hands. Okay. So, let me give you a poker hand. And I'm going to assume you have some familiarity with playing cards, just a traditional 52 card deck of playing cards. And we're going to talk about 5-card poker, just because it's difficult enough. And here's what I'm going to do. I'm going to write a hand. So suppose I get a hand where my first card is an 8. So that would be, we would call the cardinality. The cardinality would be the numbers 2, 3, all the way up to 10, the jack, queen, king, and ace. So let's say, and then they have a suit. I'm going to put an H. That would be an 8 of hearts. And then maybe I get an ace of clubs. How about a jack of diamonds? Maybe another ace, maybe another 8 of spades. And finally, how about this? An 8 of clubs. Now, when you look at this hand initially, look at that, we have a pair of 8s, don't we? Now, here's what's interesting about a poker hand. Watch closely. Now, you gotta remember, in cards, there's always appearances, the sleight of hand. But I'm not doing anything illegal, so watch the sleight of hand. Are you ready? Here we go. I'm gonna write this as, now imagine you're playing cards, you wanna throw off your opponents, and you maybe take this card here. Shoot, put this card over here. Well, what might happen? You might have something like 8 of spades. Let's put that one there. Then let's put the 8 of clubs. And then let's put all of our 8s together, the 8 of hearts. And then maybe we'll just go in ascending order. We'll put the jack of diamonds and then the ace of clubs. Well, wait a minute. Now, initially I said that we had a pair of 8s here, but really what did we have? We had 1, 2, and if you look all the way over here, there was 3 8s. This is a 3 of a kind. But then what did I do? I reordered it. Remember, I reordered it. The ordering does not matter. When I reordered my hand, it's the same hand. Either way you look at this hand is called 3 of a kind. 3 of a kind. And that is why we have combinations. So, let's try this. Let's see if we can find out how many ways you could get any 3 of a kind. Not just an 8s, but it could be any 3 of a kind. So let's try this. So let's write that. How many ways to get a 3 of a kind?
You wrote how many's?
Thank you.
Oh, I noticed earlier you said 2 of a kind. You're like, oh look, we have a pair. I let you go with it because I saw your example later that you had like a full house. So that's why I was like, where's he going with it? But
Yeah.
I think you meant 3 of a kind. I'm sure though.
I did. Yeah, and that's why I came back here.
Okay, good.
Right. Yeah, no, you're okay. So, how many ways? Thank you. How many ways to get a 3 of a kind? Okay, let's look at this. For a moment here, let's just write, I'm going to write this down very carefully. I'm going to write this, we have our 8, spades are 8, clubs are 8, of hearts, jack of diamonds, ace of clubs. Now, jack of, that's a D. I don't know what letter that was. Jack of diamonds. Now, here's here's a couple of different things I want to think of. I'm going to think of this as a few things. One is I'm going to think of that there as my 3 of a kind. So I'm going to label it as a T, 3 of a kind. This jack and this ace are just other cards. Now, no one else, if you only had if you had one 52 card deck, no one else could also receive a 3 of a kind of eights. So these cards here would be insignificant. So let's just call them other cards. O and O. And let's keep that in mind. We'll come back. The next thing you want to do is think of this. How many eights are there really? Or if these were all 4s, how many 4s are available to us, or how many 8s? There's actually 4 of them available. So we would say, for the 3 of a kind part, that we need 4, there's 4 cardinalities available, of which we need to choose 3. 4, choose 3. Okay, now, it gets a little bit better though, too. Because you could get a 3 of a kind with 3 8s. Oh, let's be more systematic. You get 3 2s, 3 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s, jacks, queens, kings, aces. There's 13. This right here, the 3 of a kind part, can happen 13 different ways. And again, you're going to multiply. That's all we've done. Now we have a dilemma. You have a dilemma. What about this other piece right there and there? Well, think of this. Let's say you're taking a look at each card as it comes. You've got 2 8s. Pick it up, you get another 8. If the next card is an 8, then you don't have a 3 of a kind, you have a 4 of a kind. So we can't get another 8 in this hand. In other words, of the 52 cards we started with, 4 cards now can no longer be accessed. So the jack, or this piece right here, can be any of 48 other cards. This is, if you could think of it as 52 minus the 4, or 48, times, well, wait a minute. Let's say we get a jack. This card can't be a jack anymore. I mean, none of the jacks are available. How many cards are left to us now? There's 52. 52 minus 8, or 44. 44 cards. Oh, I'd like to say we're done. We've done a lot of work. But there's one piece we need to keep in mind. And that was the very beginning of the problem. And it's so important. Let's put it in green. What is 2? 2 is a word. And the fact of the concern in 2 is that we have repeats of the O's. Well, how do we treat the repeats? We would treat the O's, the repeats of the problem, by just counting them, 1, 2. So we would divide all this by 2 factorial. And so, there it is. The problem is 13 times 4 choose 3 times 48 times 44. Divide that by 2, and you get your total number of 3 of a kinds. And this is why we have combinations. All right, thanks for watching.